Okay, this is the final assess of the entire course, Unit 3, Chapter 24, the assess, location 357, if you want to go there. Now it says here, sketch the graph of y equals 3. Question 1 this is, I'll probably do them all. Sketch the graph of y equals 3. Now if you look at the other page there it is. Right, y equals x cubed, it's only a sketch. There it is, it's a characteristic beautiful shape, and there's a little kink in it around the point 0, 0, then up it goes again. That's it, so that's the sketch done. 1a. Now sketch the graphs of all these, so I've got 1, 2, 3, 4, 5 graphs. That's something on the screen there. Let's just give that a little wipe. There you go, it's gone bye-byes. Right, I've now got to sketch the graph of x cubed plus 2. You may recall that if I'm going to go for y equals x cubed plus 2, I'm essentially going to take the y equals x cubed graph and lift it up 2 units. In other words, translate the function y equals x cubed using the vector, and we're going up 2 units in the air, so it's going to be 0 along and 2 straight up. Alright, so imagine that's the point 0, 2 there. It's not accurate, but I'm going to aim for, just make this a little bit thinner, I'm going to aim for that coordinate there, so that'll be 0, 2. The important thing is that I pass through it like so and label it. So that's the key point where the graph crosses the axis. The y-axis, in fact, that's the x1, is going to be 0, 2. Even though it may not be exactly 0, 2 on my sketch, I've indicated it as being 0, 2, and therefore it is a deliberate point through which I've made the new transformed function pass. So this is my original y equals some defined function of x, and this will be my y equals some defined function of x add on 2. And if you remember, it's plus or minus what we call the a, and the a value is worth 2, such that I raise the thing 2 units up in the air, or 2 units along the y-axis in the y direction. So I translated the function y equals x cubed, and I used the vector 0, 2 to do it. Very easy. What's the next one? Well, y equals x cubed minus 2. That means drop it 2 units. So here's another graph, and if that's the point 0, 0, I'm going to drop it 2 units. It's going to pass through there. So let's just do that quickly. Try and work parallel to the other one. Pass through, and that's my new function. Y equals x cubed minus 2. So what have I done? I have translated the function y equals x cubed, and I've used it. I've used the vector translate the function using vector 0 minus 2. Alright, so I've dropped it down 2 units. Fair enough. And I must highlight the key point there. That will be 0 minus 2. Again, it doesn't have to be accurate, but if you point to it and call it 0 minus 2, it's very clear to the examiner you've deliberately dropped it 2 units. Is that alright? So again, this is my original function, y equals some sort of function of x, and this is the transform one, y equals some sort of function of x. That will be plus a, but of course the plus a doesn't mean to say it goes positive, it means that it can take a negative value. So y equals function of x minus 2 because a happens to be negative. Straightforward. Let's go back a couple of places and get it. Right, next one, y equals 2x cubed. Here we go. So I'm now going to go for y equals 2x cubed. If we decode it, that's the original function, y equals f of x. And now I've got here y equals af of x, and of course my a value is 2. If you recall, if we have a 2 in front of the function, what we're doing is we're leaving the x coordinate as is, but then we're multiplying the y coordinates of each point times 2. So if we take this point here, for example, imagine that's a certain x value right there. Whatever that is, I double it up. So I'm going to put it around here somewhere. Whatever that is, I double that one up. So that's like 4 blocks. I want to go another 4 blocks from there. 1, 2, 3, 4. And if that is Oh, it's going to go way off the scale, isn't it? That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's about here somewhere. So what we're looking at is something like this. A much sharper, pointier looking graph. Of course, you don't have to plot these points, but what's happened is I've got a stretch in the y direction, okay, from here to here. That's the original, but then from here to here, it's a stretch in the y direction by scale factor 2. Why is that? Because my a value is 2 and I multiply the y part of each coordinate by 2. Sorry, that's not very straight, but it looks about right, doesn't it? From there to there, 4 squares. From there to there, 8 squares. I've stretched it in the y direction by 2. Similarly here, from here to here are 2 squares, and from here to here, right there, is another 2 squares. In other words, I've stretched it by times 2 in both directions. I've taken the graph and gone like that, and that's what it is. It's a stretch in the y direction by scale factor 2, and that's my description. And my new equation, of course, is going to be y equals 2x cubed as opposed to just the 1x cubed. What's the next one? Right, next one, half of an x cubed. Right then, it's still an AFX. Let's think about that. So this is my general function, y equals some defined function of x. Now I want to go y equals 1/2 of an x cubed. Look at it carefully. I go y equals AF of x, and this time my a is 1/2. What does that mean? It means I've now got to multiply the y coordinate of each coordinate by 1/2. In other words, it's going to flatten downwards. So if this is, for example, 4 units like we had before, then this coordinates will be transformed to here. Is that fair enough? So instead of being like, for example, 4 something, it's now going to be 4 half of that something. Alright? By the same token, if that's, let's have a look, 1, 2, 3, 4, 5 units, then that'll be just 2.5 units down. So that's that. And so we're looking at some transform function, looks a little bit like this. Still passes through 0, 0, and over it goes. Alright, so that's what's going to happen there. So if you like, this has been pulled downwards by half a unit. Is that fair enough? So that's gone down from here to here, and that's, if you like, a stretch, and also likewise this one has been pulled upwards in the other direction. And let's have a look from here to here. It's called, let's write it up here, I think. It's going to be a stretch in the y direction using a scale factor of 1/2. In other words, multiply the y coordinate by half, and that's exactly what's going to happen. Alright then, so that's that. So it's like I've taken it, instead of stretching this way, I've squashed it that way. If I go back here, look, I've squashed it that way. So it's fattened out that way a little bit. Can't use better English than that, I'm afraid, but I hope the picture says it all. There it goes. It's all been pulled outwards, it would seem, but I haven't pulled it down. I've just merely squashed it up a little bit more. And so this branch gets pulled down, this branch gets pushed up, and looks sort of fatter and wider. So I've got y equals 1/2 of an x cubed. That's that one done. What's the next one? Y equals -2x cubed. Now there's two things going on there. Let's just get on with it. I'll show you how to do it. Right, I'm going for y equals -2x cubed. Now there's two functions going on here. The minus x cubed part means reflect it in the x-axis. The 2 part means stretch it in the y direction. So putting it all together, I'm trying to stretch it in the y direction by a scale factor, using a scale factor of -2. Alright, so let's try and put this into normal English. Let me just reflect it first of all. Okay, so a reflection. So in other words, I'm going for y equals -x cubed first. So let's have a look. This branch gets reflected into the x-axis, something like that, say, and this branch gets reflected into the x-axis, something like that, say. Now the next thing I need to do, so that's going to be my y equals minus x cubed. The next job will be to then stretch it by a scale factor of 2 in the current position. So if you like, if instead of going from say minus 3, 3, the 3 in that direction must be doubled to 6 in this direction. To make that look a little bit prettier, let's just have a look and count 6 squares up. 1, 2, 3, 4, 5, 6. So I'm looking at something like that roughly. And let's try this one. 2 squares down and another 2 squares down. So I'm going to go for something like this. So this is my actual answer. So I'm coming at it like this, passing through 0, 0, coming through that point there, and then going away. So if you look at the blue one, for example, the half transformed function, I have reflected the original black line, the y equals x cubed, in the x-axis and got the blue transformation. Well, that's only half the answer, because the blue one is minus x cubed. That looks a bit more like a 3 now. Oh, it's got to be blue to match. So go for blue quickly. There it is, minus x cubed. That's the reflection. And now I've got the minus x cubed. I can then stretch that negative transformation in the y direction by a scale factor 2. And that's what's happening here with the red one. And the red one is the required answer. That is y equals minus 2x cubed. So let's try and write what happened here. So it's going to be a reflection in the x-axis followed by a stretch in the y-axis, sorry, not y-axis, sorry, a stretch in the y direction. Oh, I'll just redo that. Stretch in the y direction. Oops, that's the phone. Using scale factor of 2. Alright, I think that'll be the same as a stretch in the y direction using scale factor of minus 2. Now I just want to check that one in the answer book and then get back to you. Again, what I've done is correct. I've reflected it first, hence the blue one, and then I've stretched it. Or I can stretch it and flip it in one go, and that's the equivalent to a stretch in the y direction using scale factor of minus 2. And I'll be back, I promise. I promised, didn't I? Yeah, it says here, graph 5, it's a one-way stretch in the y direction, scale factor minus 2. Well, if you're happy with doing it in one step, great. I personally prefer to reflect in the x-axis and then stretch scale factor positive 2. It makes better sense in my brain rather than to reflect it and stretch it. Seems crazy to me. But anyway, that's correct, and that's question 1 done. Then I'll prep the others and we'll head towards the finishing line together.